Yeah, so this is the example problem I was going to work yesterday. But so the idea is that there's a linkage, and there's linkage AB, and then this corner bracket, and then linkage CD. And what you know are the dimensions of everything. You know the length from B to C is zero point 0.6 meters, is vertical length, and the length between A and B is zero point 0.3 meters. And I didn't draw it to scale, but you know that this ought to be twice as long as this over here. And we know that the length between C and D is zero point 0.9 meters. So the what you're given is that omega CD is the rotation, the rate of rotation is a counterclockwise rotation at 2 radians per second. And when it's rotating from right to left, it's decelerating, or it's accelerating in the clockwise direction at 4 radians per second squared. And what it's asking you to find is the acceleration of AB. So this linkage right here, the acceleration of it. In solving these problems, the first thing I'd recommend doing is thinking about what's going on, because unfortunately, you know, you work with these, you only have a figure at one point in time. So let's draw it. I'll draw some vectors to show you a small time later. But what you'll come up with, if I do, I'll do red lines, I suppose. So here's a small time later. So the bar will rotate counterclockwise, bar CD will rotate counterclockwise, and the corner bracket, it must, the angle between in here must be steady, or it must remain constant. So this, what's going to happen is that this linkage will move from right to left, but it'll be a fixed angle up in here. So it'll move from right to left, but the fact that this linkage AB is quite a bit, it's only a third the length of the distance between C to D. Again, it looks like half the length, but I didn't draw it to scale. So it's really only a third of the length. So we look at it, and if I drew another line, what you'll observe, or what would happen, is that the angle between A and B is actually quite a bit bigger than the angle between C and D. So what we'd expect is this counterclockwise rotation, omega CD, is 2 radians per second. It's got to be something greater. AB's got to rotate more quickly than linkage CD. And what we also know is that the acceleration, if this is decelerating at 4 radians per second, this has to decelerate more quickly. Try this on your own maybe. You might pause it right here, but I want you to try to find the instantaneous center of rotation for link BC. And do it by construction, or do it by geometry. So I'll do it, and BC, the first thing you do, we'll look at the velocity of B moving at this instant in time. It's going to be moving from right to left, and C is also going to be moving from right to left. So let's do, we'll construct a couple of lines, and I'm going to draw a line that's perpendicular to this direction. So here's a 90-degree angle, and I'm going to draw another line that is perpendicular to this velocity, and this is another vertical line. And the IC is located, these things, they're parallel lines and they never cross, so this is another right angle. Parallel lines, they never cross. The IC is located up somewhere up at infinity. So there's no finite value, finite location for the IC. And that's really important. I'll write out the relative equation for VB. So the velocity of B is the velocity of the instantaneous center plus the velocity of B relative to the instantaneous center. Of course, at some moment in time, the velocity of the instantaneous center is equal to 0. So the velocity of B relative to the instantaneous center, we know, is just the cross product between the angular velocity of BC with the position of B relative to C. So what we know, the position of B relative to the instantaneous center. So what we know is that the instantaneous center is some infinite value, or some infinite distance away from point B. So what we know is that the position of B relative to the IC is approaching infinity. And the velocity of B, of course, isn't infinite, it's some finite number. And so because the position of B relative to the IC is infinity, this is finite. That means that the omega, the rotational velocity, has got to be 0. If it wasn't 0, then we'd find out that VB was infinite. So it's got to be 0 in the k-hat direction. So I'll continue along this line. I'll write out the velocity for VB, and that equals VC plus the velocity of B relative to C. So we're looking at B relative to C right now. plus the cross product, again, omega BC with the position of B relative to C. We know already that omega BC, so the rate at which this bracket rotates, has got to equal 0 simply because the position of the instantaneous center is infinitely far in the vertical direction. So what that tells us is that the velocity of B has got to be equal to the velocity of C. So we look at it, the bracket's simply moving from right to left at this point in time where both of these things are vertical. It's moving from right to left. C is moving from right to left, and B is moving from right to left at the same rate, simply because the bracket's not rotating. So let's continue. The velocity of C, if we do it, so we know, one thing that we do know is the angular rate at which this bracket point CD, this component CD, is rotating at 2 radians per second. So we know that, so let's write out an expression for VC. And that equals negative 1.8 meters per second in the I-hat direction. I just wrote them both up here for convenience. So with that, think about what else you can calculate if I move this back up again. Take a moment, calculate what you can from the beginning, if you would, and I'll write it out for you. So one thing you can find easily enough is the acceleration of C in both the normal and in the tangential direction. And in the normal direction, or both of these you've seen before, is we know the angular velocity squared times the position of C relative to D is equal to the normal component of acceleration of C, and then this angular acceleration times the distance will give us a tangential component of C. So to clarify, what I'm talking about is this point up in here. There's some tangential acceleration moving in this direction, and there's some normal component of acceleration. The normal component, negative 3.6 meters per squared, moving downward in this direction. Oh, I'm sorry, to clarify, the tangential direction is actually accelerating from left to right in this direction. And the reason it's accelerating from left to right, it's actually, we might say it's decelerating simply because the angular rotation is in the clockwise direction. So another thing you can find off the bat is the acceleration of B in the normal direction, simply because we know the velocity of B, and write out this equation. We've got the velocity of B squared over the distance between B and A, the position of B relative to A, and calculate a value, in this case negative 10.8 meters per second. The normal component of this, because it's rotating in a circular motion, the normal component of acceleration is in the downward direction. So the centripetal acceleration towards A. But we don't know just yet the acceleration of B in the tangential direction. We know it's also got to be, from left to right, just because C is also from left to right, and it's connected by this bracket, so I'd expect, some velocity, or some acceleration from left to right for B. So next thing, let's apply the acceleration equation, and this comes from the relative acceleration. So the acceleration of B is equal to the acceleration of C plus the acceleration of B relative to C. And we can break this one into tangential and normal components, and the tangential component is simply the angular acceleration crossed with the position vector, and the normal component is this omega squared times the distance. So let's take it, write it out in vector form. So I put it in brackets here to fill in, because eventually we'll get a couple of equations to work with. So the acceleration of B in the I-hat direction is the acceleration of B sub t. We don't exactly know it yet, so let's just put it in. It's a b sub t. And I'm going to do the same thing for the j-hat directions, negative 10.8 meters per second squared. One thing I've done is gone between normal and tangential components. So then the tangential component we know is going to be in the I-hat direction. So we're talking about the acceleration, point B, the acceleration in the tangential direction is in this direction, and that happens to be, in this case, coincident with the I-hat direction. So that makes the trigonometry pretty easy. And then in the j-hat direction, the normal component's got to be downward in the j-hat direction. One thing we know that simplifies life is that omega bc has got to be equal to 0. So this whole term we don't have to worry about in the acceleration equation. So let's evaluate this term, the cross product between alpha and RBC. So alpha, a vector quantity. I wrote it out here if you'd like to see it. So we don't know alpha bc. It's something we'd like to find. And what's interesting, while we do know that omega BC is equal to 0 at this point in time. It's not actually rotating, but there's nothing preventing it from accelerating. So if you look at this thing, what happens is this piece will rotate down more quickly than this piece. Or I'm sorry, this piece will rotate down more quickly than this piece, and you get a rotation in this direction. So there is some angular acceleration. It starts at 0 and it'll accelerate simply because this part of it's moving more quickly than this part, or will end up moving more quickly than this part. So working through the determinant on this, we get a negative 0.6 alpha BC in the j direction, and in the I direction we get positive 0.6 alpha BC. So we've got what we got now. We've got a way to evaluate this. We'll eventually put this vector form into this equation. So the next thing we can do is fill in the blanks for the acceleration of point C in both the I and the j directions. So we knew from the beginning the acceleration of C in the j hat direction. We know the acceleration of C, the tangential component, in the I hat direction. So we know both the normal tangential components for this. So I'll just move them down below. So let's assemble everything. We've got the acceleration of B, we'll put in here the vector quantity. We've got the acceleration of C, we'll put in for that term, and I'll write it out down below. So I've got the acceleration of B, I just moved this into here. We still don't know the tangential component, but we're in a nice position now to find it. I moved this component in for alpha BC into these first two terms, and then the third term, the acceleration of, oh, I'm sorry, so I moved these into, so both of these were moved into these two terms, and alpha C is represented by these two terms. So let's get a system of two equations, two unknowns for both directions. So let's deal with the I hat direction first. We got this unknown quantity, we've got this quantity, and we've got this quantity. So we can relate the tangential component of the acceleration of B to alpha BC. And then what I can do is relate the j hat component. So we know this has got to equal these two terms, the two j hat terms. So we got two equations, two unknowns, and solving for alpha BC, come up with 12 radians per second squared, and then in the tangential direction the acceleration is 10.8 meters per second squared. Finally, what we end up with, you can solve for alpha AB because you know this relationship. The acceleration in the tangential direction is equal to the angular acceleration times the length. We'll solve for alpha AB, and what you come up with is 10.8 meters per second squared divided by 0.3 meters. We come up with a value of 36 radians per second squared, which is in the range. The hint I was going to give you in class was that it was somewhere between 25 and 45 rads per second, so we're within range. And it's a positive, or it is in the clockwise direction. So I've omitted the signs on this. It is in the clockwise direction. So we go back up to the figure. So you know, because CD, even though it's moving to the left, it's decelerating, it's slowing down, and the acceleration at this point is in the positive or the clockwise direction. The acceleration of AB is also in the clockwise direction. It turns out alpha AB is equal to 36 radians per second squared.